today's date, which is Friday, 2/26/21. The next time I see you guys, it'll be March. That's so weird. Our topic is exponential functions. So we're going to start out with the definition. An exponential function is a nonlinear function in the form of y equals ab to the x power, which isn't going to mean a lot to you right now, but it will as we work our way through the packet. Okay, so of course there's a couple rules. A cannot equal 0. B cannot equal 1. And B has to be greater than 0. You're going to see this symbol a lot, f of x. What does f of x mean? Who remembers? Adam.
Y.
It actually means y. Right? It's just fancy. So anytime you see f of x, just remember it's a fancy way of saying y. Because it's what did you do to x to get the value, and that value happens to be y. That's our input-output situation. So don't let it confuse you or overwhelm you. It's just a fancy way of saying y. So the first thing you're going to do on Monday's assignment is you're going to look at tables and you're going to determine if they are considered linear functions or if they are considered exponential functions. Okay. What do we know about linear functions? They have a what? Adam?
Pattern.
No, we're not going to use the word pattern. I know what you're thinking, but we're going to stay away from the word pattern, and you'll understand why in a second. They have a constant rate, Ben?
Constant rate of increasing or decreasing.
Of change. Yep, constant rate of change, right? Exponential, Adam, has a pattern, but it's not by adding or subtracting. It's by multiplying or dividing, and that means it's not going to be a linear graph. Okay, so underneath linear, put addition, subtraction. Underneath exponential, right, multiplication or division. Is that what you guys use for multiplication, a little dot? Or would it make you feel better if I put an X? I don't see X's make me nervous because they look like.
X's make like a little star.
Oh yeah, the star, the little asterisk from everyday math. Isn't that what they used? Little star.
Please do not give me PTSD.
But isn't that what they used? I taught that like, gosh, I don't even know, like 20 years ago. Okay, you get the point. All right, so let's look at A. Somebody tell me, would this be considered linear or exponential based on the changes in x's and y's? Ethan? It is going to be linear because we are adding by 2 for our y's and we're adding by 1 for our x's. So this would be linear. And we can write ourselves a note, constant rates of change. All right, and then for B, what do we see happening for our x's? What's happening there? What's our Ben?
They're increasing by 1.
Okay, and then how about our y's? What do we have happening for our y's? Multiplying by 2. So this is where it's a pattern. It's a cool pattern. It's dependable. We know the next number is going to be 64, but that doesn't make it a line on the graph. It actually makes it look like a curve, right? So this would be exponential. Graph would curve. Okay, so look at table 1 here. Is that going to be linear or exponential? What do you think, Bryce?
Linear.
All right, so Bryce, why do you think it's linear?
Because subtracting. Y is subtracting by 2s.
Is it subtracting by 2s? It's dividing by 2s, right? So 8 divided by 2 gives me 4. 4 divided by 2 gives me 2. So the x's are increasing by 1, which makes you think, oh great, this is going to be linear. But then you got to look closely and make sure the difference between each thing is the same for it to be linear. So this is going to be exponential. How about table 2? What do we think here? Linear or exponential? Who haven't I heard from? Olivia M. It is linear because we are subtracting 1 for our y's and adding 4 for our x's. That's adding and subtracting. We're going to get a straight line if we were to graph that. Okay. Now, I have had students in the past that this never makes sense looking at the tables. So what they will do is they'll just do like a little sketch out to the side and be like, all right, 0, 8, 1, 4. And you'll see how this is going to be graphed as a curve, or you would see how this would be a straight line. So if you're having trouble just looking at the table and making the decision, you can always do like a little sketch of a graph out to the side. So that's our first set of information for today. The second is evaluating exponential functions. Make sure you have your calculator either on your phone or your iPad, the scientific version, ready to go. So what we're going to do is we're going to be substituting in values. Okay. So if I have this exponential function, first of all, how do I know it's an exponential function? What does it have? Ethan?
It has like the y. It has like the same thing that like the exponential function, like the y equals a to x.
Yeah, and it's got an exponent, right? That x happens to be an exponent in this situation. So what we're going to do is substitute 3 in for x. So we're going to say y equals negative 2 times 5 to the 3rd power. And then I'm going to get y equals negative 2 times 125. And then what will be my final answer? What is the y value? Atlee?
Negative 250.
Yep. Okay, so we'll do another example right here. Now, I'm going to highly encourage you guys, don't assume you know what's going to happen when you're doing exponents with fractions or decimals. Don't assume. So always use your calculator, right? I don't want you to be that person being like, oh, well, I thought for sure it was this. Well, if you had checked with your calculator, you'd know that wasn't what it was supposed to be. So remember how we do this because we've been practicing with our growth and decay. We're going to put negative 2 in there, so I'm going to get y equals 3 times the quantity 0.5 raised to the negative 2 power. Then I'm going to put in 0.5. I'm going to choose that x to the y button. I'm going to put 2 and then hit the plus minus sign to make it negative. Then I'm going to hit equals. So now I have y equals 3 times 4. Did any of you think that that was going to be 4 right there? 0.5 to the negative 2 power was going to give you positive 4, right? So just make sure you're not assuming things, right? So then I think we can all do 3 times 4 without a calculator, and you get 12 for your answer.
Can you do the calculator again? Mine keeps saying error.
Okay. So tell me what you're putting in your calculator. Like, walk me through what you're doing.
So I was doing negative 2, and then I click like the x to like the y power thing,
Mm-hmm.
and then I put 0.5.
So you have to put the 0.5 in first.
Oh.
So you have to do 0.5, then x to the y, and then 2 with the negative sign. And then you'll get your 4.
Okay.
Yeah. Okay. So let's go ahead and take a look at this next one. I didn't give you the x values yet. I want you to solve when x equals, or evaluate, negative 2, 0, and 1/2. So we're going to do the exact same thing we've been doing this whole time. We're going to do y equals 2 to the 9th to the negative 2. This one gets a little weird. You're going to get kind of, if you do 9x to the y, 2 negative, you're going to get this funky decimal. So my advice would be to just immediately do that times 2. You're still going to get a weird decimal, but you don't need to write down that middle step each time. So I'm going to get y is about 0.2. Excuse me, 0.02. Notice I have the squiggles because it's not an exact value. So then I'll do y equals 2 times 9 to the 0 power. If you can't remember what anything to the 0 power is, maybe you want to put that in your calculator. Who remembers? 1. So we're really going to get y equals, oh, this is supposed to be positive 2. 2 times 1, so we get an answer of 2. And then our last one, y equals 2 times the quantity 9 raised to the 1/2. So I'm going to do 9, x to the y, 0.5, and I end up with y equals 2 times 3, y equals 6. How are we feeling about using a calculator? Everybody feel pretty savvy, the order and everything? Okay, so for number 4, I want you guys to do the same thing. Substitute in x equals negative 2, 0, and 1/2. So I'm going to freeze my screen. You can go ahead and work on this. Obviously, our at-home viewers, it doesn't freeze your screen, so maybe pause the video and check back. I'm going to work these out, and we will compare. You're doing all 3 of them.
Okay.
The negative 2, the 0, and the 1/2.
Right. Are we doing one of the numbers or letters?
So you're going to substitute in negative 2, 0, and 1/2 for x. We're doing number 4.
Okay.
Yep. Sorry, no, you can't see that right there. Ready to compare?
Not yet. Give me a second.
Okay, no, that's fine. Bryce, do you have any hockey this weekend?
Yeah.
Yeah? Exciting. Do you play, okay, I think I may have asked you this already, but do you play against Henry, or you guys play on the same team? Henry?
Oh, yeah, I'm facing him tonight.
You are? Oh my gosh, it's so exciting. What position do you play?
Right now, defense.
Okay. I think he does too. Oh my gosh. That's cool. All right, here we go. Ava, you ready?
Yeah.
0.375, 1.5, about 2.12.
Yep.
All right. So you guys are ready for Monday's assignment. Now we're going to continue on the next page, but you won't be doing any of this stuff from now on Monday's assignment because we're not going to finish it. So I can't ask you to do that. All right. Graphing exponential functions. Good times. Get those color pencils ready. What we have here is a graph of the function, right? And I told you it's going to be curved. Okay, so we're just going to label some things here. So let's go ahead and label this top arrow, or excuse me, color this top arrow blue. And that, it says a is greater than 0. So we're just going to clarify that. That is when a is positive. And we'll just highlight that in blue so we remember. So I took these screenshots from the textbook. Of course, they're beautiful and they're in color, but you cannot see that in my copy. So we're going to color it for ourselves. So then the one going down, we're going to highlight red, and that is when a is negative. And remember, a is that first number in our exponential function form. Okay, so something that I need you guys to understand, don't overthink this, because I did have some students yesterday that had like all these extremely intense questions. Don't overthink this. But when you have exponential functions like this, do you see how this red line looks like it's coming up close to the x-axis and it looks like it might actually cross over? It's never going to cross over. It's just going to continue to get closer and closer, like microscopically closer to the x-axis, but it's not going to go above it. Same with this one. It looks like it's going to go below the x-axis, but it's not going to. It's just going to get closer and closer, right? So the example I gave yesterday, if I continuously divide something by 2, is it ever going to be a negative value? No, it's just going to get smaller and smaller and smaller exponentially. See what I did there? But it's never going to be negative. It's just going to be teeny tiny values. Okay, or if I continue to multiply, right? So I need you guys to write out to the side here the graph, which I'm talking about these lines that we have here, the blue and red lines, will never cross the x-axis. Okay, again, that's because we're not subtracting anything. We're just multiplying or dividing, which means that it's just going to continually get smaller. Like to our vision, it's going to look like it's on top of the x-axis because we don't have the ability to like zoom in on our, like this isn't an iPad, right? So I can't continuously zoom.
Even if it was on an iPad,
Wouldn't see it.
The pixels would just blend together.
Yep, absolutely. Okay, so our goal is going to be to do this first, graph this first function. So here's our function right here. Go ahead and color that in yellow. And that'll make sense in a second. We're going to compare this one to our parent function. A parent function is just kind of like a generic given, and then you make observations comparing your new function to the parent one. And if you notice throughout the packet, It's the same parent function graph throughout the whole packet. It's always going to be this. And it has a G there. It could be an F. It could be an H. It could be an M. Anyway, y equals 2 to the x power. Remember, that's just a fancy way of saying y. So if you look down here at your graph, let's go ahead and color this in green. That's our parent function there. I don't know if I told you guys on Wednesday how I was creating this packet while you were working. Did I tell you that?
No.
Like I was over here just like typing this up and making it. And I couldn't find a good graph for this. So I used graph paper. I drew a plane. I graphed it. I took a picture with my iPad. I sent the picture to myself. I screenshotted it. I shrunk it down. And then I put it here in this file. That's how much I care about you guys, if you're ever wondering. Those are the lengths I go, Ben, to make sure that you have a good graph, right? Because nothing online looked good, and it was taking way too long to find something. All right, so when you're graphing a function, step 1, make a table of values. So that's what I've done here for you. I've provided you with a beautiful table. Now, I'm going to expect you for all of your tables to use these 5 values, -2, -1, 0, 1, 2. That doesn't mean you'll be able to graph them all because your graph is not going to go high enough or wide enough, but you're going to create these 5 values, graph what you can, plot what you can on the coordinate plane. So, given this function, get out your scientific calculator here. Good thing we just practiced evaluating, right? If I put -2 in for x, what will my y be? Atlee? 1. Great. If I put -1 in for x, what will my y value be? Ethan? 2. If I put 0 in for x, what will my y value be? Bryson?
4.
4. You guys see what's happening here? If I put 1 in for x, what will my y value be? 8. And then I don't even need my calculator because I see the pattern. It's going to be 16. Great. So then we're going to plot these points. So step 2, plot the ordered pairs on the graph. So -2 up 1, -1 up 2, 0, 4, 1, 8. And then I can't graph 2, 16, and that's okay. Step 3 says draw a smooth curve to connect the points. So we're going to do our best to connect these with a smooth curve. And then you guessed it, we're going to color that line yellow to represent our function that we just graphed. This helps us remember which one did we start with, the parent function, and which one did we create, the yellow function. All right, now I'm going to ask you to analyze this. What do you notice about the new one compared to the parent function? What do you notice, Ben?
It's increasing at a faster rate.
It is increasing at a faster rate. So it looks like it's a little bit narrower, right? Like it's actually like steeper, right? That's called a vertical stretch. Right? So we can say narrower, steeper, right? But it's called a vertical stretch. Imagine you have like silly putty. You guys know what silly putty is? It comes in those cute little plastic eggs. And you stretch it out, right? It gets thinner as you stretch it, right? So that's why it's called a vertical stretch. If our graph had been like below and like wider, that's called a vertical shrink. And I always compare that to like when you like smush a marshmallow and it like expands, right? So it's like shrinking and it's getting wider on the out because it's like mushy on the inside. You know what I'm talking about? Yeah. Okay.
Have you ever microwaved a marshmallow?
I have.
I have.
Yes.
Oh.
Also, you can notice that the y-intercept is now at 0, 4. It was at 0, 1 when we started. So that's where we're going to leave off today.